Now that we've learned about polymorphism, there's another feature of Coq that we can put to good use. Let me preface this by saying we could have studied this feature first, but it makes more sense and is more useful in the context of polymorphism, which is why we're doing it here. The feature is higher order functions. What we mean by that is that functions in Coq are first class. Particularly, you can use a function in a place of any other value that you want. So for example, you can pass a function into another function and return a function from another function. Now, not all languages let you do such a thing. It is one of the quintessential features, though, of functional programming. It's right there in the name, really. Right? We can use functions as part of our programming in the same way as we use all the other types of values in our program. Natural numbers, lists, strings, whatever. Let me show you a simple example of this. Here's a function called doIt3times, which is going to take in, well, let's see, first a type argument x, which is implicit, and then a function f. That function has type x arrow x, so it transforms one x into another x. What are some examples of something that could be? That could be the increment function on natural numbers, right? Because that takes in a natural number and gives you back a natural number. Or it could be the negation function on Booleans, which takes in a Boolean and gives you back the opposite Boolean. Right? So this function is actually parameterized on that type x. So this is where parametric polymorphism is coming in useful. And then the function doIt3times takes in another argument n of type capital X. So obviously that's going to be something of type I could pass to f. And then doIt3times is going to give me back something of type x. And what does it do? Well, it takes f and it applies it applies it to n 3 times, right? So take n, apply f to that once, and then a second time, and then a third time. Okay, so the type of doIt3times then, if we look at it without that implicit type argument, is that it takes in a type argument x and a function of type x arrow x and a value of type x and gives us back of something of type x. Let's see a couple examples. So we could try applying the -2 function to 9 3 times. So what are we doing here? We're passing the function doIt3times, another function -2, which we wrote before. You remember what it does. It subtracts 2 from a natural number. Of course, it's truncating subtraction. And the argument 9. So -2 is instantiating f here. 9 is instantiating n. And what does that do? Well, we're going to subtract 2 3 times from 9. So 2 times 3 is 6. 9 minus 6 is 3. So that does seem like the right value. And indeed, we're able to prove that unit test there. Or we could do something with negation on Booleans here. What happens if you negate true 3 different times? Well, you take true and then flip it to false, and then true, and then to false. So that unit test does go through as well. So what's interesting about parametric polymorphism here is that we're using it to pass in a function whose type is not a fully written down type like the ones we've been using so far, right? We don't have to say that it's a function of type nat arrow nat or bool arrow bool. Instead, we get to parameterize even the type of the function on that. Let me show you some examples of functions that are really interesting in this space. In fact, some very famous kind of higher order functions that you're going to want to know by name. One of them is filter. So the filter function, which exists in many functional languages, standard libraries, is something that we'll define here on lists, although it makes sense for other data structures as well. Filter is going to filter out all the elements of a list that either satisfy or don't satisfy some test predicate that's passed in. Okay, so let's look at the types involved here. We're parameterizing filter on a type x. We're passing in a function named test, which takes in a value of type x and gives us back a bool, gives us back either true or false. So think of this as like testing for the elements of the list that we want to keep. If an element passes that test, we're going to keep it. If it fails the test, we're going to filter it out. And we pass in a list of elements of that type x, and we get back a list of elements of type x. But of course, the idea is that we've filtered out the elements that didn't pass the test. So how do we code that up? We can match that list. If it's the empty list, then we'll just give back the empty list. There's no elements to filter out. But if it's the list containing head, cons, tail, then we will test the head. If the head passes the test, then we keep the head element and cons onto it the result of the recursive call. So we continue filtering the tail with that test predicate. Of course, if the head element does not pass the test, then we don't return it, sort of drop it on the floor, as it were, and continue with the recursive call, filtering out all the rest of the elements in the tail that don't satisfy the test and returning the ones that do. So that's the filter higher order function. Here's some examples. Suppose you wanted to filter the list 1, 2, 3, 4 through the even test. You should keep only the even numbers, get rid of the odds. That's exactly what filter is doing here, as you can see by the result of that unit test. Or suppose you wanted to filter on a different predicate. Here's a new one. This test function, length is 1, as the name suggests, is determining whether the length of a list is exactly equal to 1. Remember, we use the comparison operator here on the natural numbers, equal question mark for that. So if we filter this list with the predicate list is 1, then we're going to keep only the elements of that list, which themselves are lists of length 1. So we get rid of 1, 2, we keep 3, we keep 4, we get rid of 5, 6, 7, we get rid of the empty list, we keep 8, and that gets us the list containing the lists 3, 4, and 8 as singleton lists. So here you see some of the power of filter going on. We didn't have to write filter specialized for different types. We get to write it parametrically with respect to whatever the type of the underlying list is. And in a different sense of parametric, we've parameterized the function on the test predicate that we want to use. So we didn't have to hard code a particular filter function for only even numbers or only lists whose length is 1. We get to factor out that test that's supposed to be used by filter. That's really powerful in the sense that we've divided the labor between two different people. Think of it as follows. There's someone who's responsible for coding up the list library. They're the person who has to write things like filter that know how to iterate over elements of that library, keep some, maybe transform some, do whatever. We'll see some other examples of functions like this later. And then there's clients of the list library, people who just want to use the data structure and do something with it. They're the ones who are going to have an interesting idea for what kind of tests they want to run on elements of their lists. So the division of labor here is that the person writing the list library writes the code that iterates over the list. The person using the list library writes the functions they want to use to take elements from a list or do some other things, as we'll see in a second. Okay. Here's one more example. Suppose you wanted to count the odd members of a list. So now we're actually plumbing together all of the things that we've just seen. We could take a list, filter out all the odd elements of it, and then take the length of that list. So let's see. Count the odd members of this list here. Well, I see 1, 3, 1, and 5. So there's 4 of them. And indeed, that unit test should go through. Good, it does. Count the odd members of 0, 2, 4. There's 0. Count the odd members of just the empty list. Nil. There's 0. Okay. So we're able to put filter to use like that, along with other functions to do complicated, really, kinds of transformations of lists, but express them very succinctly just in terms of these functions that we're using. Length function, filter function, the odd function. You don't have to code this up like maybe you would in an imperative language with a loop that kind of hard codes all of these things, like looping over the elements of the list, testing whether one's odd, like computing the length of it. You would probably do that with a function in most imperative libraries. Okay. Now, in the examples we just saw, we were passing in functions we define as the test predicate, right? So we defined count odd members prime and had to pass that in there. We defined length as 1, had to pass that in there. Earlier in another chapter, we defined even. You don't always have a use for one of these test functions everywhere else in the body of your code. Like maybe this is the only place in your entire code base you're going to write length as 1, or maybe the only place that you're going to use odd in your entire code base, for example. In situations like that, you don't even need to give the function a name. You could directly pass in the function anonymously to filter or to other higher order functions. Let's see how that works. The idea here is that functions can be constructed sort of on the fly without giving a name to them. And you do it with this syntax that we're going to look at. So suppose I wanted to do something 3 times, which is square a number. So suppose I wanted to square a particular number 3 times. In this case, it's 2. So I'm going to square it again, and then square it again. And I should get 256. Okay, because I go from 2 to 4 to 16 to 256. That does indeed go through. But what is the syntax that I used here? Well, I'm writing what's called a lambda expression. You can see it even starts with the Greek letter lambda here. It's another name for a lambda expression is an anonymous function. This is a function that takes in an argument that's written after the lambda and then returns whatever's on the right-hand side of this arrow. So that arrow is part of the syntax here. So you can think of like, this is the input, this is the output of the function, and the arrow is sort of indicating like a transformation that's going on. We're transforming that input into that output. Okay, so you can read this as the function that given a number n yields n times n. The notation here comes from mathematical logic in the 20th century. In particular, a mathematician named Alonzo Church invented this. You'll find it all over the place in programming languages theory and in mathematics as well. So the expression that we wrote there was a fairly simple anonymous function. Of course, they can be as complicated as you would like. Here is an anonymous function that takes in a list L and determines whether the length of that list L is 1. So that's really the anonymous function corresponding to a function we wrote up here. Length is 1, right? But I didn't have to write out this whole long definition. Now, arguably sometimes for software engineering purposes, you might want to write out a definition like this, particularly if you're going to use that function repeatedly throughout your code base. But if this is the one and only place you're going to use it, it might be simpler just to write it as an anonymous function, as I did here. So I could filter out exactly the elements whose length is 1, and that gets me the list 3, 4, 8, as it did before. All right, so that was filter, one of the most famous higher order functions. In the next video, we'll look at a couple other very famous higher order functions.